In this video, I wanted to examine the general derivative of a logarithm because we already know that the derivative of the natural log is 1 over x, which we did implicitly. And I wanted to show you, well, how could we solve the derivative of any base instead? And so what we could do is use the change of base formula, which is what I like to call log law number 4. But let's go ahead and recap that real quick. But let's say we have a logarithm base a to the x. Logarithms always have the property that we can change their base to whatever we want, but basically the property is it's every logarithm of any base of the x is equal to log of the input divided by the log of the base. And this property works for anything. A lot of times it's written as base b, but I wrote it with a common log. But another way I could write it is using a natural log. It's equivalent no matter what ratio. It doesn't matter what the bases are. It's equal to a ratio of those particular the input divided by the base. So basically the log base a to the x is equal to the natural log of x divided by the natural log of a. And if you're kind of lost or you don't believe me, let's check it out. So in your calculator, you have the log base function. So let's just say we wanted to know what is log base 2 of 7. And again, what this would represent is, well, 2 to what power makes 7, which is not, it's going to be irrational. And 2 to the, approximately 2.8 power would give us 7. Again, that's what a logarithm does. But what the change of base formula says is that if we rewrote this as ln, this should be equal to the natural log of the input divided by the natural log of the base. Let me just demonstrate that this does work. But anyways, and why is that helpful? Well, basically, if we're trying to, the goal of this video is to determine the derivative of log of any base to the x, because now that we've kind of looked at the derivative of exponentials of any base, same thing, we want to know in general what's the derivative of a logarithm. But basically we could rewrite our function as the natural log of x divided by the natural log of a, or equivalently speaking, we could also write this as 1 divided by the natural log of a times the natural log of x, because as a fraction, you can always split the numerator off from the denominator. Like if you have 1/2 times 3, it's equal to 3/2. And well, why am I writing it this way? Well, again, if we're trying to solve the derivative, my point is we already know the derivative of, let me go ahead and write that once again, but in the previous video, we know the derivative of the natural log of x is 1 over x, which we did implicitly. And actually, I'm going to ignore the instructions from our lecture notes and just do, because it's basically we already know this derivative is 1 over x. So if we know that the log base a of x is equal to 1 divided by the natural log of a times ln x, well, the derivative of this is just 1 over x, and this is just a coefficient. This is just a constant number. This will not change when I'm applying the derivative of it, because this is just like let's imagine this is like a number like 0.3 or whatever it is. 0.3 times ln. If I know this derivative, the coefficient rule for derivatives will not affect the derivative. That's another derivative rule that we looked at a long time ago. But anyways, this will not affect the answer, and the derivative of ln x is 1 over x. And again, this is a little bit of a different strategy than how I had planned to do it in the notes, but this, in my opinion, this is just a lot easier way of showing it. And this is just the answer, or I could write this as 1 over x ln a. And this is the general derivative of logarithm function of any base. And why I think this is actually pretty easy for me to remember, because if you look at the derivative of a general exponential function of any base, you don't do anything. The derivative of the x is the same, but it's just multiplied by the natural log of a. Notice that the derivative of a logarithm is very much the same. The general derivative of the natural log is 1 over x. But if I want to change it to another base, say log base a, I need to multiply 1 over x, the denominator, by the natural log of a. But basically, notice the consistency here is it's the same derivative. It's divided by the ln a instead of multiplied by the ln a. And that's because we're dropping 1 over x in our derivative of the logarithm x. And those rules are backwards because exponentials and logarithms, they're inverses. Their rules often work very opposite to one another by design. And if you look at the next page, that's exactly what this is. The general derivative of log base a of x. Sorry, that's like an underscore, but didn't come through very well in the packet. But it says it's 1 divided by ln a times 1 over x. Or again, you could just write that put together as 1, because obviously 1 times 1 is 1, and ln a times x is x ln a, as I like to remember it. But in the same sort of way, we could then solve various derivatives now that we know the generalized process. So, for example, what is the derivative of log base 7 of x? Well, basically, again, how I remember it is start with the natural log, it's 1 over x. Now, if the base is different, I need to compensate by the natural log of the base. So here we have base 7, so I'm going to have 1 over x times the natural log of 7. And this would be my exact derivative by rule. And again, this is easy in my opinion to remember because it's kind of the same as an exponential. As you know, if I was looking at 7 to the x, its derivative is 7 to the x ln 7. I'm just multiplying by the natural log of 7. But when I'm taking the derivative of a logarithm of, again, the inverse of the same base, those are kind of similar, they're almost the same function, just backwards. The derivative is same as its normal condition, 1 over x divided by ln 7 instead of multiplied as the very opposite. And so say we wanted to know the derivative of the common logarithm. Remember that common log is usually meant to mean base 10 when there is no subscript, except for in very specific, some sources actually use this as base e, which is a little annoying, but it's just, you got to know what base it is. But in most mathematical text sources, this refers to base 10. And so that being said, you can pretend there's a 10 there, or you can even write it in. But if we're using this rule, that's my point, is you would need 1 over ln 10, because that is our base of the common log. So we'd have 1 over x ln 10 would be the derivative of the common log function. And say we had to do, say, we want to know the derivative of x squared times the common log or whatever else. Again, we would need the product rule. So let's practice that. It would be first d second. So first is x squared, keep it the same, multiplied by the derivative of the common log is 1 over x ln 10. Then plus second d first. And the derivative of the first is just 2x. And so in the first expression, x squared over x, we could actually simplify that because those are just normal algebraic entities. X squared divided by x is just x, and then divided by ln 10. So I would have x over the natural log of 10 plus, and remember when it comes to logs and algebraic expressions, these will not multiply, you can't multiply x into 2x because this one is attached to the log. So usually we just write the 2x in front of an expression like that. And this is probably one of the nicer ways I could write that. I could even factor out x, which is a common factor if I wanted to. And doing one more, in the last example from the packet, it's asked, okay, what's the derivative of log base 3 of 2x minus 5? Well, basically, again, this is another chain rule example. And again, I know I'm very repetitive with when I teach you guys the chain rule, but in my opinion, the chain rule is one of the more difficult ones to figure out. But I always like it as inside as outside. And how I recognize that I need to use a chain rule is I have something on the inside of the logarithm. Anytime I have anything other than just x on the inside, I need to use the chain rule in that context. So I think about what's on the inside and what's on the outside. And in this case, I always take the derivative of the outside first. So I'd start with the derivative of log base 3, which is 1 over x times ln 3. So I'm going to have an ln 3. And remember, we're keeping the inside the same. So here, 2x minus 5 is taking the role of x in this equation, right? Because x, I'm being replaced with 2x minus 5. So if I'm taking the derivative of log base ax, I need to do, this is the whole derivative. So I have 1 over ln a times 1 over x, or 1 over ln 3 times 2x minus 5. I'm replacing it. Or remember, as I say, the insides should stay the same. And that would be the derivative of log base 3. However, I also need to multiply by the derivative of the inside. That's the last step of the chain rule, the thing that's super easy to forget to do. But the derivative of the inside, that's just 2, because derivative of 2x minus 5. But cumulatively, this would be our derivative of log base 3 of 2x minus 5. And it gets a little bit tricky because there's a lot of rules that are kind of at play at the same time. and we got to be very careful about applying them in the correct order. But again, I could write that 2 on top because 2 times 1 is 2, of course. So I'd have 2 divided by 2x minus 5 times the natural log of 3, and that I could leave my derivative as such. So that will wrap up this online lecture module. I know the algebra gets a little bit tedious when it comes to logs and exponentials, but it's important. Really, what I would say is it's important that you remember your basic formulas for derivatives of logs and exponentials, because when we're in the realm of calculus and we want to solve rates and derivatives and tangent lines and all the stuff that we've learned to do in calculus, it's important that we know how to solve our derivatives. That's like the whole thing, right? That's the whole point of the class. And when we finish up with chapter 2 on Friday, next week we're going to start chapter 4. We're going to talk about what we call antiderivatives and integrals. And if you don't know your derivatives, then again, just like in any other part of calculus, if you don't know your derivatives, you're up the creek. So either memorizing them is the suggested way of going about it, but in these videos I really wanted to give you some examples of how to do it and also why are the derivatives what they are. Anyways, see you all next class.